Today's problem was submitted by a viewer, and it says, point A exists in the two-dimensional plane at coordinates 0, 0. It has starting velocity v is equal to 10, 10. You shall choose a direction at which constant acceleration of 1 unit per second squared will apply. Find such a direction so that the point A would intersect 50, 100 eventually. Okay. Yeah, so it's basically like, basically a physics problem. So to clarify exactly what it is we're going to do, the magnitude of the acceleration is a constant, but we get to choose the direction. Think of it like a uniform gravitational field. We get to choose which direction gravity pushes us. And we want to make it so that the trajectory of the particle eventually goes through this one point. So my thought here is just to set up a full coordinate system. We have the initial position and the initial velocity. The acceleration, the acceleration is a vector. We can write down the equations of motion, and we just want to find the particular value of acceleration that puts us through this point. Okay. Let me draw a coordinate system like this. So we have the initial point there. V0 is equal to 10, 10. And the acceleration, I'll even put it as vectors like that. The acceleration, it has a magnitude of 1. So the acceleration will be cos theta sine theta, where theta is the angle that the acceleration vector makes with the horizontal axis, like that. And now we just write down, I'm going to write down the equations of motion. So v as a function of t is going to be 10 plus cosine theta t times cosine theta. And in the y direction, it will be 10 plus t times sine theta. So if theta is equal to 0, then the acceleration is purely in the x direction, and that's 0, and the y component of velocity will always be 10. So if that's the velocity as a function of time, then the position as a function of time will be, in the x direction, it'll be the integral of vtx from, I guess I'll call it v, let's call it, well, I can write this out properly. It'll actually be the integral of the vector vu du from time 0 to t, like that. So vu is 10 plus u cos theta, 10 plus u sine theta du. So in the x direction, we've got 10t plus t squared over 2 cosine theta, 10t plus t squared over 2 sine theta. Okay, so this is the position of the particle as a function of t for any angle that the acceleration goes through. And what I want is I want this point to eventually intersect the point 50, 100. So I need 10t plus t squared over 2 cosine theta, 10t plus t squared over 2 sine theta. This should equal 50, 100. And so of course this is really just two equations and two unknowns, right? Well, I suppose the best thing to do is take a difference of these two equations. You know, let's not think of it as a vector equation anymore. Let's actually just think of it as two equations like this. I'll do the bottom equation minus the top equation. I mean, this looks like a double angle formula of some sort, but yeah, solving these equations is going to be more difficult than arriving at these equations. Maybe instead, here's a better way of doing this, I think. I'll treat both of these as quadratic equations. So let's write it as cosine theta over 2t squared plus 10t minus 50 equals 0. And sine theta over 2 times t squared plus 10t minus 100 equals 0. So I need, my thinking here is that, I mean, the other approach I had where I took a difference of these two equations, maybe that could work out in some way. I didn't see it. What I'm going to do is treat this as a quadratic equation for t, write down the roots. Treat this as a quadratic equation for t and also write down the roots. Well, we need the roots to coincide, or at least we at least need one of the roots to coincide. And based on the phrasing of the problem, we should probably take t to be positive. So if this has a positive root and if that has a positive root, we need those two positive roots to be the same, and that should give us a relation between sine theta and cos theta. So from the first equation, we have t is equal to negative 10 plus or minus the square root of 100 plus 100 cosine theta over cosine theta. This is not, it's uglier than I expected it to be. And so we're going to take the positive root. And from the second equation, we have something similar. We have negative 10 plus the square root of 100 plus 200 sine theta square root divided by sine theta. Okay, we need these to be equal to each other. Let's factor out a 10 from everywhere. So negative 1 plus 1 plus cosine theta over cosine theta is equal to negative 1 plus 1 plus 2 sine theta cross multiply. I don't see I don't see an easy simplification anywhere. I mean, based on the geometry of the problem, we could probably rule out a few things, like the initial direction of the particle is well, it's moving 10-10, so 45 degrees, but the point we have to reach is up here at 50-100. So we know the acceleration should probably have a larger vertical component than horizontal component, right? I mean, here's a relation which, in theory, gives us a value of theta. And then we're done. I mean, at this point, it turns into if there are any trig identities or anything like that which can conveniently solve this. You know, another way of thinking about this is plot that as a function of theta, and plot that as a function of theta, and look for an intersection. I don't know if there's a way to solve this with a formula. So I've taken a second to simply plot these two expressions I have for t as a function of theta, and this is what I immediately see. So we don't see an explicit crossing of the two curves, but it looks like there might be a point where they just barely touch here. And in fact, it looks like that happens when theta is equal to pi. It's about 3.14. So what I'd like to do is just verify by hand that if theta is set equal to pi, we get a solution for these two equations. So if theta is equal to pi, let's call this T1 and T2. Then T1 is equal to negative 10 plus 100 plus 100. Cosine of pi is negative 1. So that's actually gone. T is equal to 10. And T2, when sine theta is equal to pi, or when theta is equal to pi, I guess, do we have to work this through as a limit or something? Hold on. If theta is equal to pi, then this equation is correct. This is correct. But we don't have a quadratic equation anymore. Okay, so technically, yeah, obviously my quadratic solutions here, these rely on those denominators being non-zero. So if I go back up to my system of equations, if theta is equal to pi, then the first equation becomes 10t minus t squared over 2 is equal to 50. And the second equation becomes 10t is equal to 100. So we know this one already gives t is equal to 10 from the equation below with, well, here. Substitute pi, theta is equal to pi, you get t is equal to 10. And here you also get t is equal to 10. Yeah, so the acceleration you need, in fact, is pointing exactly in the negative x direction. Maybe there's a way that you can see that cleverly from what's given. I mean, setting things up with this coordinate system or first principles and stuff works. I was a little bit sloppy in that by writing these down, by writing these two equations down, I'm assuming that those things are non-zero. Perhaps what I should have done is made a few guesses as to what theta could possibly be. And we know that we can rule out certain regions. The acceleration, if the acceleration is anywhere in that direction, we're never going to hit that point. And if it's straight down, if it's that way, if it's that way, if it's that way, we'll never get to that point because the trajectory will always sort of, I guess, be moving downward, right? But just trying a few values of theta to see what happens maybe is a good guess. I'm not sure exactly what the source of this question is from the viewer. But I mean, yeah, and I also don't know. Yeah, I guess this might not have panned out. This relation might not have led anywhere because it came from a system of equations where we assumed that sine theta is non-zero. But I'm not sure if I don't see like an analytical way of deriving the correct answer here. If the question were changed in such a way that the point we're trying to hit, if the point we're trying to hit is not 50, 100, but say 55, 95, then your nice convenient guess of theta is equal to pi, isn't going to work. But maybe there's another approach, another sequence of computations. Maybe what I'd done earlier with, taking a difference between these two equations, maybe that would lead to something. I don't really know. But yeah, theta is equal to pi works. It's a cool problem, I think. Like it tests whether you really understand how to set up the coordinate system for something like this. But it'd be nice if someone could let me know if they can actually derive, like do a sequence of computations that arrives in theta is equal to pi, rather than essentially making a guess or just plotting something and seeing that, we conveniently end up with an intersection of these 2 points at pi. Yeah, thanks for watching.